Hello grade 10 students, I hope you're good and safe. I'm Rewa Jirdi. I'll be teaching you biology and chemistry for this year. The first chapter we're gonna start with is the atom. As we took previously in grade 9, an atom is the smallest particle of an element that retains the property of the element, which means that an atom has the same property as the element it belongs to. Atoms are made up of subparticles or of smaller particles that are protons, electrons, and neutrons. As we take a look at the model of an atom, we can see protons and neutrons inside the nucleus, where electrons move in orbits or shells around the nucleus. So, protons and neutrons are found inside the nucleus, while electrons move around the nucleus. Z is the number of positively charged particles, which means that Z is the number of protons or the atomic number. As we observe the adjacent figure, we see 6 positive charges inside the nucleus, which means that this atom has 6 protons, then its Z is equal to 6. In a neutral atom, the number of protons is equal to the number of electrons, always. So, when there is 6 protons in this atom, then automatically there is 6 electrons and you can count them. Electrons are distributed on shells or energy levels or orbits, we call them. As we know, neutrons have no charge. They have 0 charge. What is the role of the neutrons inside the nucleus? Neutrons increase the stability of the nucleus by eliminating the force of repulsion between protons. As we know, same charges repel each other. Plus and plus repel or reject each other, while plus and minus attract each other. So inside the nucleus, there are only positive charged elements. So to decrease the repulsion between positively charged particles or protons, to decrease the repulsion between protons, neutrons do this, okay? Representation of an atom. Also, as we took previously, an atom is represented by XAZ, where X is the symbol of the element, A is the mass number that is equal to Z plus N, and Z is the atomic number, the number of protons. It is the identity of the atom. We know that this atom is carbon because its Z is equal to 6. It has 6 protons. Each atom has its specific number of protons. So 6 protons automatically belongs to the element carbon. So C is the symbol of carbon, 12 is the mass number that is A, 6 is the number of protons that is Z. Again, A is the mass number, A is equal to number of protons plus number of neutrons, that is Z plus N. N is the number of neutrons, as we said. To calculate N, you move Z to the left side, so N equals to A minus Z. Now, determine the number of neutrons in the adjacent carbon atom. N is equal to A minus Z. A equals to 12 and Z equal to 6. So 12 minus 6 equals to 6. Then the carbon atom has 6 neutrons. 6 neutrons, 6 protons, and mass number equal to 12. And by this, since I said it has 6 protons, then automatically we know that it has 6 electrons. How to calculate the charge of the nucleus? Now, let's take a look again at this atom. We can see that it has 6 positively charged particles, which means that it has 6 protons. So its Z is equal to 6. Q is the charge, okay? Q belongs to the charge. The unit of the charge is in coulombs, C, denoted by C. Charge of the nucleus is equal to the number of protons times charge of a proton. So, charge of the nucleus equal to the number of protons, that is Z, times charge of a proton, that is plus E. Okay, we know that protons are positively charged. In this figure, Z is equal to 6. So it is 6 times charge of the proton is 1.6 times 10 to the power minus 19 plus 1.6 times 10 to the power minus 19 since it is positively charged. You multiply 6 by 1.6, the result is 9.6, then you add to it times 10 to the power minus 19 in order to make the calculation simpler. So you leave 10 to the power minus 19, you bring it down, and you just calculate 6 times 1.6, the result is 9.6 times 10 to the power minus 19 that you already brought down. Stoner rule. Stoner rule is used to know the number of electrons on each shell. How many electrons are there on each shell? We use Stoner rule by applying the formula 2n squared, where n is mainly less than or equal to 4. That is what we're gonna use. Now n can be 5, 6 or 7, but we mainly use till 4. Let's take an example. N equal to 4. N is the energy level, okay? N equal to 4. 2 into n squared. 4 squared is equal to 16. 4 times 4 equal to 16. Then you multiply the 16 by 2. The result is 32 electrons, okay? These electrons on each shell are distributed on subshells or on sub-energy levels, which is different from the way we used to distribute electrons in grade 9. In grade 9, we used to distribute electrons on energy levels K, L, M, and N. Now it's different. We have sub-energy levels or subshells that are S, P, D, and F. S can be filled maximum by 2 electrons, P can be filled maximum by 6 electrons, and D can be filled maximum by 10 electrons. F is filled maximum by 14 electrons. Let's take an example. N equal 1, which is 1 energy level. N equal 1 energy level. N belongs to the energy levels. We replace the 1 by N. 2 into 1 square by applying Stoner rule formula. 1 square is 1. 1 times 2, 2 electrons. So it is S2, since S can be filled by maximum 2 electrons. Another example is the second energy level, which is N2. Replace the N by 2. So it is 2 into 2 square. 2 square is equal to 4. 4 times 2, 8 electrons. Let's distribute them on the subshells. S fits maximum with 2 electrons. So S2, P6, okay? S2, P6. P can be filled with maximum 6 electrons. 2 plus 6 is equal to 8. This is the sum of electrons. N equal 3, third energy level. Again, we replace the 3 with N. So 2 into 3 square. 3 square is 9. 9 times 2, 18 electrons. Let's distribute them on the subshells. 18 electrons. S2, I cannot pass from S to P unless I fill S with its maximum electrons. S can fit with maximum 2 electrons, so I put it S2. P6, 2 plus 6, 8. I still have 10 electrons to fill. So S2, P6, D10 by order, SPD. Okay? N equal 4, which is the fourth energy level. Again, we replace the 4 by N. It is 2, 4 square. 2 into 4 square. 4 square is 16. 16 times 2, 30 equals to 32 electrons. We have to distribute these 32 electrons on the subshells. S2, P6, D10, they are 18 electrons. Still 14 electrons. I put them on F14. I hope it's clear for you now. You can practice it at home. Now let's talk about Kleshkovsky rule. Kleshkovsky Kleshkovsky rule is used to fill the electrons of each atom on each shell according to their energy. And here is the pick. N equal 1, so I'm talking about the first energy level, 1. Subshell is S. S fits with maximum 2 electrons, so it is 1s2. When we talk about second energy level, which is N2, it has 2 subshells, 2s2, 2p6, 2s2, 2p6. N equal to 3, 3s2, 3p6, 3d10. Okay, 3 energy levels, S, P, and D. And I put the number of energy level before the subshells, 3s2, 3p6, 3d10. N equals to 4, 4s2, 4p6, 4d10, 4f14. Now, as the number of energy levels increase, the subshells do not increase. I only have 4 subshells that are S, P, D, F. N equals to 5, 5s2, 5p6, 5d10, 5f14. N equals to 6, 6s2, 6p4, 6d10, 6f14. N equal to 7, 7s2, 7p6, 7d10, 7f14. So as we can see, as the number of shells increases to more than 4, the number of subshells do not increase. I only have S, P, D, F. N equals to 1, I have S. N equal to 2, S and P. N equal to 3, S, P, D. N equal to 4, S, P, D, F. Beyond this, the number of subshells do not increase. Now, if you take a look at the red lines, this is Kleshkovsky rule, the way we should move with this electron configuration. I'm going to give you an example. Keep this Kleshkovsky rule in front of you because you're going to use it in doing the electron configuration. Here it is. For example, I have Cl17. Cl has Z equal to 17. I should distribute these 17 electrons on the subshells. I start by using Kleshkovsky rule in this way. 1s2, 2s2, I start from the right to the left. 1s2, 2s2, 2p6, 3s2. Okay, let's count the electrons now. 2 plus 2 plus 6, 10, plus 2, 12. I still have 5 electrons. So, I put 3p5, not 3p6. If I put 3p6, then I will have 18 electrons, which is not the case. Okay? Another example is calcium that has Z equal to 20. I should distribute these 20 electrons on the subshells. I start using Kleshkovsky rule. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Follow the arrow. Follow the arrow, okay guys? 4s2. Now let's count them. 2 plus 2, 4, plus 6, 10, plus 2, 12, plus 6, 18, plus 2, 20. Here they are, okay? Now, how to determine the column and the row? If the electron configuration ends with S1 with 1 electron, S1, then it is in column 1. If the electron configuration ends with S2, then it is in column 2. If the electron configuration ends with Px, like P5, then it is in column 12 plus 5. It is in column 12 plus 5, then it is in column 15. Okay? If the electron configuration ends with Dx, D2, or D10, then it is in column 2 plus x, 2 plus 10, 12. Okay? I hope it's clear. You should memorize these. Another example, Na11, Z equal 11. I distribute the electrons on the subshells 1s2, 2s2, 2p6, 3s1, not 3s2. I have one electron only to fill, so I put 3s1. S1, then it is in column 1. And since the highest energy level is a 3s1, it is a 3, the highest energy level, the highest n is 3, then it is in row 3. Lewis dot symbol for sure is based on the number of column. Column is 1, so we put 1 dot for Na, okay? Another example is P15, Z equal 15. I distribute the electrons on the subshells 1s2, 2s2, 2p6, 3s2, 3p, not 6, 3p3, since I have 3 electrons only to fill on the p. Okay, so you guys tell me, it ends with p, then it is in column 12 plus the electrons on the p. 12 plus 3 here, it is equal to column 15, and it is in row 3, since the highest n we have reached is the 3, then it is in column 3. Again, Lewis dot symbol is based on the column, and since it is in column 15, then there is 5 electrons on its outer energy level, and we can count them 3s2, 3p3. We add the electrons of the same shell of the same n, 3 and 3, it has s2 and p3. S has 2 electrons and p have 3 electrons. 2 plus 3, then p have 5 valence electrons. And this is it, column 15, we always add 10. So column 15, then it has 5 valence electrons, not 15. Okay? This will become easier in the practice that we're gonna make.